We're back again. This is chapter 29. The video lecture today concerns itself with the photoelectric effect. The photoelectric effect occurs when light is shining on a metallic surface, giving up to electrons in the metal sufficient energy for them to escape into the air. So here is an edge view of a metal-air interface, metal below, air above. That's an electron sitting at the surface of the metal. It's about to receive a photon energy equal to E. When it does receive that energy, if it's enough energy, it will escape into the air with a certain kinetic energy. This is how the kinetic energy it has is calculated. It's equal to the energy of the photon, that is to say the energy that the electron absorbs, minus this quantity W. That W is equal to the amount of work, or we could say the amount of energy the electron that is at the surface has to give up in its fight to break the bonds that keep it attached to the metal. And that amount of work is called the work of function. Somewhat of an archaic term, but for historical conventional reasons, we'll continue to call it the work function. But the work function is just the energy in the electron that's already at the surface of the metal has to use to get away from the metal and fly away with some kinetic energy. And so we now know how to calculate the kinetic energy of the electron that makes it into the air. Let's look at a simple example of potassium metal, whose work function is 2.0 electron volts. Let's shine ultraviolet light on it. Lambda is equal to 100 nanometers. You don't need to know why that's ultraviolet light, it's just so. 100 nanometer light, we wish to calculate what the kinetic energy of escaping electrons are. Well, you may recall from the previous lecture the 1243 equation, a very valuable equation that quickly allows you to know what the energy of photons are if you're told what the wavelength of light is that contains those photons, and vice versa. Tell us what the energy of the photon is, and we can tell you what is the wavelength of the light that contains those photons. Get it? All right. Well, in this case, the energy of our photon is 1243 divided by 100 nanometers, or 12.43 electron volts. Now, from this equation, we calculate the kinetic energy that the electron has is what's left over after it uses 2 electron volts to fight its way away from the surface. Final result, the kinetic energy is 10.43 electron volts. Now there's a second part of this problem. What's the speed of the electron that has been photoemitted from this potassium metal? Question mark. Continues up here. I report to you the mass of an electron, 9.11, 10 to the negative 31 kg. Now, in our speed calculation, we will be working with standard units, expecting to get our speed in meters per second. And so we will need to calculate the kinetic energy the electron has in standard units, not electron volts. No, joules. And so let's do the following conversion from electron volts to joules. We have here the kinetic energy is 10.43 electron volts, but each electron volt is that many joules, the 1.6 10 to the negative 19 number. Final result for the kinetic energy in joules is this 10 to the negative 18 number. That's the kinetic energy our electron has. It's the 1/2 mv squared value, where m, shown here, also up there, is the mass of an electron. 1/2 mv squared equals the kinetic energy here. Solve this equation for V, and this is what I got. I hope that's what you will get too. Now, let's ask a different question. Suppose that in measuring the kinetic energy of the electron that escapes, we end up finding that it's only 9.43 electron volts. Our calculations show it should be 10.43. Well, what will have happened is that the electron whose kinetic energy we measure flying out here, in fact, did not start out at the surface. The electron that absorbed that photon of energy was actually at some location deeper within the metal. Those electrons can also absorb photons striking or incident on the metal surface, and there's a possibility they could escape into the air. Well, what evidently happened is that 1 electron volt worth of energy is missing, and we should pretty much know where that 1 electron volt of energy went. An electron that was below the surface down here somewhere is the one that absorbed the photon worth of energy. And so before it has a chance to escape from the surface, using, as we now know, an amount of energy equal to W, it has to make it to the surface first. And to do that, it has to burrow its way through the atoms of the crystal, of the solid, of the potassium. And evidently in this case, the amount of energy the electron had to use to get to the surface in the first place was 1 electron volt. So the answer to the question, in this case here, how much energy did the electron that was deeper within the metal use to get to the surface? The answer is simple. 1 electron volt. I hope that's clear. If not, watch the video again. That concludes this video lecture. We'll have more to say about Chapter 29 material in our next exciting video lecture.